Looks like no more people are coming. Therefore, I think it's the right time to start. So, people who know me from this school know now that keeping time budgets is my specialty. So I will need to go a bit more quickly on the next part. The material is available. I'm available. If anything seems unclear, get back to me. This is a numerical computing course, which means that we are going to spend a lot of quality time with numbers. And that means you need to know how numbers work in Rust. We have so-called primitive types, which are essentially types that are meant to map into either machine operations or stuff that's really easy to emulate using machine operations. We have fixed size and size integer types. Unlike in C, they don't have a very long name that's annoying to type. Just the minimum amount of information you need. U for unsigned, number of bits. People are happy. They go from 8 bits to 128 bits in multiplications or 2. If you are familiar with modern hardware, you may wonder where is your hardware with 128 bits. Actually, it's on the RISC-V roadmap. You may get some someday. But the reason why this type is here, even if it will almost always be emulated on real hardware, is that we often need to do operations on 128 bits integers in the real world due to things like universally unique identifiers, for example, and IPv6 addresses. Because of that, compiler authors have spent an enormous amount of time implementing good emulations of 128-bit arithmetic on top of 64-bit arithmetic. And since we have it, it would be a shame not to use it, so it's exposed in the language. Then we have usize. That's an unsigned integer that is as wide as a pointer on your architecture. So if you're on a 32-bit system, it's 32 bits. If it's a 64-bit system, it's 64 bits. You need it because sometimes when you do terrible things that you probably shouldn't be doing, you need to turn pointers into integers and back. And also sometimes you need to do also terrible things like counting how many elements you have in an array, and this is kind of pointer size dependent as well. We have sign versions, we have the usual floating point suspects. Sorry, Vincent, no 80 bits. But the good news is we don't have 16 bits either yet. They are on the horizon, however, along with 128 bits floating point numbers because some hardware actually has support for this. And even when you don't have it, your compiler can do it pretty efficiently as well. Literals, it's quite similar to C++11. We replace the backtick with underscore because people think it's more readable. I personally agree, but its style, people will disagree. You don't need suffixes because Rust did not follow on the C mistake of making literals typed. So your integers are as wide as they need to be. Almost. You don't get performance traps linked to your floating point number accidentally turning to double precision when you didn't intend to do that, because we don't have implicit conversion. As you will see, this has an ergonomic cost. So the jury is out on this one, whether it was worth it or not. I personally think it is, due to the 20 times slowdown I mentioned earlier. So there are no implicit conversions, because implicit conversions are bad in both directions. We have narrowing conversions. Most people agree that these ones are bad. The problem with narrowing conversion is that you lose information. So for example, if you have an integer which is larger than 256 and you cast it to an 8-bit integer, you lose information. You should do that explicitly, and you should check also that it's a correct operation. And then we have promoting operations, which increase the size of the type. And people have a harder time seeing why this is a problem. This is one of the reasons why I added an example in my profiling course to show how exactly this can become a performance problem, a very big performance problem indeed. So you don't want either narrowing or promoting conversions, which means you want no implicit conversion. The code will be a bit more verbose, but it will be better for it. This means that you will have to do this sort of casts often. So these mostly follow the C rules, but without the undefined behavior. As you may not know, in C, if you take nan and you say, no, nan is an integer, you have a problem. In Rust, it's a garbage integer, which is better, I guess. Still, people are unhappy about those because even if they are explicit, they introduce the same risk as before. And some people think that the syntax is a bit too easy, a bit too concise, and people are going to do it without thinking about what they are doing. That's why for many operations now, we have more verbose, more specialized alternatives that let you be very explicit about what you do. Like, for example, you can take a 64-bit integer and say, I want to turn this in an 8-bit integer if it's a valid 8-bit integer, and otherwise I want to report an error. Arithmetic is almost the same. We don't have the tilde bitwise not operator that C has because we don't need it. Since we don't have implicit conversions, there is no Boolean equality, meaningful Boolean equality on integers. So we can just reuse the not operator that we already have to do bitwise not on integers. Because we have no implicit conversions, you cannot write integer factors in your floating point operations. Sorry, it must be a floating point factor. I've been through that. I know it's hard. Trust me, in about a few weeks, you will get the hang of it. What happens when you do incorrect arithmetic? In C and C++, there are some operations that silently produce garbage, and other operations that produce undefined behavior, which means that the compiler is allowed to assume this doesn't happen and trash your program in an arbitrarily bad way in case it does happen. With undefined behavior, remember, anything is possible. Rust tried to improve upon this. The problem is here that operations on integers or floating points are very fine-grained operations. They are very performance critical, and that means now you need to be careful about inserting checks on these sort of things. So what they ended up doing is saying, okay, this time we will do the bad thing and have different rules in debug and release builds. In debug builds, all arithmetic is checked by default. If you do something that is stupid, it's an error, your program will crash at that point with a nice stack trace. In release build, it will silently produce a wrong result as in the well-behaved types in C++. And there are no ill-behaved types. There is no undefined behavior possible with just arithmetic alone. Still, you know, people sometimes actually want to do the wrong thing, the thing that hardware does under the hood. And that's why we have more specialized operation. Like, for example, people who do signal processing will be very happy to know that we have stuff like saturating addition. That's very convenient when you do the stuff like audio processing. We also have wrapping, detect errors, all the varieties of arithmetic you may want, depending on what precisely you want to do. Rust is not C++. You do not need to be a struct or a class in order to have method. Every type gets a method. If you define a type, you can add methods to it. The standard library uses this to implement methods on all basic numeric types, which means that you can do stuff like this, like if you want the length of the hypotenuse of a triangle, rectangle, triangle, you can take one side, square it, take the other side, square it, and compute the square root. Now, if you have the same education as I do, you may think, okay, this is great, this is horrible, how do I change that? You can. And the way you do so is because the standard library did not want to do it due to the fact that prefix operators break type inference. You need to do it yourself. I have done a small library that does it for you. Exercise, I will not get into this. Loops, because again, this is numerics. We love to iterate. The basic syntax, maybe, you know, if you've been doing some Python before, it's basically Python in different syntax. So the default is ranges that are left inclusive write exclusive, which means that this will print integers from 0 to 9. If you want to know why it's up to 9 and not up to 10, I think I have put in the course a link to a very detailed discussion from one of the pioneers of programming, Hadrien Grasland, that explains why this is the best way to do loop bounds. I will not get into this sort of debate. I have used languages that use all the kinds of loop bounds, even the most stupid one, and I've managed to write my loops just fine, but okay, to some people it matters. If that's your kink, I don't kink shame. Rust does try to accommodate people from different backgrounds, which means that if you come from the Fortran and Julia crowd, where write inclusive bounds are the common case, you can have them. It's just a matter of putting an equal sign on the right side of the range. You will not get one-base array indexing. Sorry, you still need to adjust to that, but that's really something, I guess. These are not the only kind of ranges that exist. You can have infinite ranges, ranges that start at a certain value and go infinitely far, ranges that come from the minimal value of the type and go to some value. If these combinations are not good enough for you, you can have any combination of infinite bound, inclusive lower bound, exclusive lower bound, and same with upper bounds. It will just be a dirty tuple to show you that you're doing something dirty. Actually, loops like that are not hard-coded in the language. One of the first things the compiler will do with your code when it sees this sort of loop is it will take the expression here after in, and it will call the into iter method on it, which will take whatever you have specified and turn it into an iterator or die trying. Once you have an iterator, you can do iteration. That's what they are for. And in Rust, it looks like this if you do it explicitly. So you call the next value of the iterator. It gives you either some value or none to tell you that, OK, iteration is finished. You really need to stop now. Why do we have this? And why don't we have the beautiful iterators of the C++ STL where you need to type begin and end everywhere? Well, I think my sentence just answered the question. It's a model that is very hard to use right. It's very easy to get undefined behavior with it. It's not helpful. It doesn't chain to multiple operations. It's garbage. That's why 5 years after the release of Rust version 1.0, the C++ committee finally agreed it's garbage. Let's throw it away and replace it with iterators just like Rust because they're just better. Unfortunately, my colleagues who tried to use it were telling me in the past that it had some big performance problem. I think they are checking right now if the performance problem is finally fixed. I hope so, because these iterators are awesome, and once you get used to them, there is no going back. So what do we get by having self-sufficient iterators that know what is the end of the iteration? What we get is iterator adapters. All iterator objects in Rust get for free a bunch of methods that let you transform the underlying stream of data. For example, if you iterate initially from 0 to 100, you can turn that into the iterator and say, OK, now I want to step by 10, which means that I want code which is logically equivalent to taking the first value, skipping 9 values, taking the 10 values, skipping 9 values, and so on. It looks like this. In the end, what you would expect. Remember, iterators are still write exclusive. Ranges are still write exclusive. So, one very important property of these iterators, which was also inherited by Rust ranges because they basically took the copy machine and tried to do their best with the limitations of the C++ type system, is that these are lazy. Until you start putting them in a for loop or a similar construct, they do not start iterating over value. When the compiler starts compiling your for loop, it knows the entire pipeline. And this means that you can get very high quality compiler optimization, which is to say that when you write something like this, it's exactly equivalent to the Python range that has this third 10 argument that you may be used to in Python. It will have the same performance, it will, well, better than Python obviously, but it will compile to the same code you would have written with the I plus equal 10 loop in C, which is very nice. Then, you know, we are not forced to iterate over ranges. We have other types that can be iterated upon, such as collections. The first two collections that I will introduce, because it's a tradition in programming language courses, is arrays and heap allocated arrays, which, if you have been doing C++, are std array and std vector. So same differences. Std array arrays in Rust are allocated in line. If you put a variable of type array in the middle of the function, it's allocated on the stack. If you put it in the middle of a struct, it's allocated inside of that struct. It does not require a separate heap allocation. The size of arrays must be known at compile time, because otherwise you just broke the compiler ability to calculate the stack layout, and then your program performance becomes terrible. And also you may create security vulnerabilities that way. Look up why the Linux kernel forbids VLAs for details. As in C and C++, you must be careful with stack allocated arrays. That should only be used for relatively small arrays. Because most operating systems, for stupid reasons, put a bound on how big your stack should be, even if they don't have to. And that means that you will, at some point, reach the limit of the stack and crash your program in a manner called Stack Overflow. Also, you know, I'm the profiling person. I must say this. If you have big arrays in the stack, you break perf as well. Please don't break perf. Perf is super useful. Because arrays need to know their size at compile time, you must restrict yourself to the set of possible sizes that can be computed at compile time, which means it has many annoying limitations. All inputs to the size calculation must be compile time. It cannot be a user parameter on the command line, for example. So it's a bit annoying to deal with when you want something more flexible. That's why my advice would be, if you don't know, use vec by default. If you find an allocation performance problem, switch to array. Use array as an optimization, or when you know ahead of time, because you are a code genius, that this is really going to be bottlenecked on heap allocations if you don't do the array thing. There are two syntaxes. You can put a list of elements between square brackets. This should not be terribly surprising to people who've used Python, say. You can use this syntax with a semicolon and a number of elements. And that's a shorthand for creating an array that has the same value repeated n times. Very convenient for zero initialization, for example. By the way, you want, if you don't know what to initialize your numeric arrays with, you should initialize them to 0 because that's optimized at the operating system level. If you are doing arrays, you have the std array from fn standard array function. It gets a function as a parameter. That function receives an index as an argument, and it knows how to compute the index element. So it will be called for the 0th element, the first element, the second element, and in this way you will construct the array. But as you can see, that starts to get in the realm of weird APIs. No, we need anonymous functions. I have not introduced them yet. Compare that to what it takes to construct a vec now. And here you see that I have a range. I want to turn it into a vec. I go to an iterator first because iterators are amazing. And then I do collect. And I say I want to collect into a vector because otherwise it doesn't know. You can turn an iterator into many things. And you get a vector that has the same content. If, like me, you prefer the so-called turbofish style, you can do it as well. By the way, the reason why I prefer it is that it puts the type right where it's needed. So I personally think it makes expressions a little clearer, especially when you are chaining more things below that.
Can we do the same thing with an array instead of the vec?
No, because iterators do not have a size that's known at compile time.
Okay.
And to do, actually, yeah, you can, but you may have runtime failures. Sorry.
What?
You can, if you specify the array hard-coded, but you will have a runtime failure if you have more elements in your iterator than there's room in the array, or less. So that's not a great experience. Again, that's why I recommend using vec by default. It's easier, and many times it will be fast enough.
Okay, and is there a way to transform a vector to an array?
I would use std array from fn for this, but it's not great. Or collect into array, but you get the same problem that you have explicit indexing, you have bound checks to know if it's the right size. It's not going to be very performant. Basically, you can go to arrays from vector, that is easy. Vector to array is hard because vector is more flexible than array. And if you have been doing C++ in the 20th century, as I have been doing, you may know that there is another way to initialize iteratively an std vector in C++. You specify a certain initial capacity, you push elements one by one. You can do that as well if you prefer. One nice thing is that unlike in C++, this is a constructor. You don't need 2 lines of code to do this. It's a nice touch. You can, again, iterate over arrays or vector. So now I can put an array on the right-hand side of my for loop. I can put a vector and it will work, because there is this implicit into iter call inside of the for loop implementation. We have indexing with square brackets, as in C++, but it works differently. In C++, can someone tell me what happens if you put an index that is larger than the length of an array of vector or equal to it? Anyone? And what happens next? What? No. You don't. No. You only get it if you use the @ operator to standard containers, because as always, C++ picks the wrong defaults. By default, what you will get if you are a bit out of bounds is you get access to the next thing in the program stack or in the heap allocation, hopefully, if the compiler has not seen what you're doing, because what actually happens is undefined behavior. The compiler assumes that whenever you access an array, the index is in bound. It will optimize your code under the knowledge that all indexes will be in bound. If your indexes are out of bound, you don't know what's going to happen. And it can change between compiler versions. Undefined behavior is bad, don't do it. I think MSVC and Windows with default configuration bound checks, but I'm even not sure of that. Yeah, so what Rust does is the same as pretty much every programming language other than C++, which is to check that the index is in bound, and if not, it's an error. Which is a problem, because you're doing numerics, lots of indexing, and on every index, you do a check. Maybe your compiler will manage to optimize this check, maybe not. If it doesn't, your code just became full of branches. So how do we get good performance out of this? And the way we do so is we don't use indexing. As I will show later, we use iterators whenever we can. If we do have, for some reason, we absolutely have to do indexing, maybe the algorithm is better expressed in that way, then we can turn to unsafe code and get the same semantics as C++. But we try really hard not to get there, because many Rust developers are seasoned C++ programmers. They've seen the harm that undefined behavior can do, and they pledged against it. Still, at this point in the course, I have not introduced the workarounds to avoid indexing when you need to iterate over 2 arrays, which, by the way, is something the C++ STL didn't know how to do until very recently. So with the tools we currently have, which is iterators, we have a trick, which is enumerate. What enumerate does is you take a sequence of things and it turns it into a sequence of tuple, where the right-hand side of the tuple is the elements of the original sequence, and the left element of the tuple is a monotonically increasing sequence of integers starting from 0. If you call that an iterator that was built out of an array, what you get is the values of an array along with the matching indices. And then you can do things like that. Still, bound check, bad, but at least you know that your iteration is correct, you are doing the correct bounds. It's a bit safer. We also have slicing, another thing that C++ stole later on because they discovered it's great. I don't know why they discovered it only then. I mean, Python has had it forever. Okay. The idea of slicing is that now you can say, I want elements of an array, for example, from this index to that index. And it takes you the subset of array in the form of a type called a slice, which, if you've been doing C, you can think of a Rust slice as a combination of a pointer to the first element and the number of elements. If you're doing very modern C++, that's stdspan. Still, problems. We are doing explicit indexing again, bound checks. Bad performance, maybe, if the compiler is not in the good mood to optimize the bound checks today. So for common patterns like stencils, which is what we are going to need in the grayscale reaction, we have iterators over slices, arrays, vectors that are specialized for common patterns. We have chunks. Chunks takes identically sized chunks of the array and may produce a remainder that's smaller at the end if your array size is not a multiple of that chunk size. Unfortunately, compilers are stupid. So if there is any chance that the chunks may not be all of the same size, they will drop the assumption that all chunks are of the same size. They are not clever enough to know that they can just split the loop in two, which shows you that really compiler technology, even after 50 years, is still very immature. And thus, you need a language-based hack, which is chunk exact, which lets you basically get only the regular size chunks with all the right black magic to tell the compiler that it will be the same size. And then you have a different way to get the remainder. If you are doing any kind of signal processing convolution, you get Windows. And I get to the question next. Is the question right? OK. Windows is not the operating system. It's the overlapping windows if you've been doing any kind of discrete convolution. Like you want the first 3 elements, then elements from index 1 to 4, 2 to 5, you get the idea. That's it. And I see we have some questions. That's people doing SQL. How is it safer to use enumerate instead of a counter variable? It's slightly safer. As I mentioned, we are going to see better tools later that allow us to eliminate all indexing. But still it's safer because let's say you have a Fortran programmer in your team and you are a C++ code base. And you have an array of size 10 and you know the Fortran programmer has the hard-coded muscle memory and they go from index 1 to index 10 and now you have a problem. With enumerate, you cannot have this problem because the indexes are automatically generated by the enumerate method, so they will be right for Rust arrays. It's a small thing, but it's helpful in specific scenarios. Again, we are going to see better stuff later on. OK. We can do loops. Great. Not very impressive. We had loops in Fortran versus 1, which by Vincent's historical account was the very first structured programming language. We want more. I will get you more. I will get you anonymous functions and fancy stuff based on that. In Rust, first of all, there are no stupid scoping rules as in C and C++. You can declare pretty much everything everywhere. You can declare types instead of functions. You can declare functions instead of functions. There are almost no restrictions, which is very convenient when you are trying to do very encapsulated code where, if other code doesn't need to know, then it doesn't have access at all. Here's an example of that. So we have a function that sums numbers in a way that's inspired by the private sector, which is to say it doesn't actually do the sum, it delegates it to a different function. And the way it does that is it defines an inner sum function that takes two inputs, produce one output, and it calls it. Okay, but Rust is not Python. So when you do that, you are not allowed to use variables from the outer scope, which is very limiting. The way we get that in Rust is using anonymous functions. Anonymous functions have a syntax that is much nicer than C++11, thank goodness. At least people sometimes learn from their language design mistakes. You get a pipe character, a set of parameters if you have any, second pipe parameter to say that's the end of the parameter list. If you want to say what the type is, you can do so with a narrow notation, like for top-level functions. And then you put the expression, and this expression is allowed to use variables from the outer scope. Because closures are meant to be used inside of functions, they get inferred types, like everything in function basically gets inferred types. But if you want explicit types, you can have them. Your choice. And next, we get to some very powerful stuff that's outside of the scope of this course, because it's one day, which is traits. In C++, which was pretty much the most advanced, the low-level programming language with the most advanced type system before Rust. You had many different ways to do polymorphism in the type theory sense of having some function operator accept inputs of different types. You had virtual methods that you can override. You had templates. And then you had a back copy of Rust traits called concepts. It came 5 years after again. I mean, ISO committee discussions take time. You had function overloading and method overloading for objects. And you had also default parameters. And you had implicit conversions. And you say, oh, wow, so flexible. There's just a problem. I know of no C++ developer that can look at a C++ expression in code and without spending 10 minutes thinking about it and furiously writing things on paper, say, this is the particular function that's going to be called in this context. When you have different polymorphism features, they interact in different ways. Some take precedence over others. And as a result, the languages become incomprehensible. That's why Rust opted instead to design a single polymorphism system that's powerful enough to encompass the use cases for all of these things and more. And that's traits. The one good thing about this is that even if you are some wizard on top of a mountain, which I have never met, which is actually capable to understand the polymorphism rules of C++, what you still get is you don't need to switch from one polymorphism mechanism to another as your code evolves and your use cases evolve. Which is good because all of these mechanisms in C++ have different syntax, which means that migration is a pain. Traits avoid that because they are powerful enough to do pretty much everything. The only circumstances in which you can get migration pain is if you had compile time polymorphism and you decide to move to runtime polymorphism. There you will have some pain because runtime polymorphism is more limited than compile time polymorphism, so you will need to restrict your code to fit into the limitation. You can still do some of the things you could do at compile time, but there are some you cannot do anymore. And when I say more powerful, by that I mean that you have some power you could not dream of in C++, except maybe, in C++ 36, if the stars align in exactly the right direction. you have the ability to use traits to add methods to types from someone else. And that's incredibly powerful. It means if you're something like TBB, which is called Rayon interest, you can have parallel iteration method on standard library types. That's based on your code. If you need some weird genericity that takes integers of 8-bit but not and 32-bit but not 16-bit, you can have it. You just create a new trait and you implement it for only those types. That's pretty amazing. And the second thing, it surprises most C++ developers, is when the C++ developers copied the trait, tried to copy the trait concept badly with the concept feature, they copied it wrong. They forgot half of the work. See, the goal of these features in both languages is to be able to tell early on that a user is passing the wrong type to a function, such that if the wrong type is passed, you get a high-level error at the point where they call into your library, and not a low-level error deep into the implementation, where GCC will tell you about 100 different functions they tried to call and didn't match. The problem is concepts try to fix this, but they fix it in one direction only. To fix this problem, you need to have two things. You need to have a mechanism for checking that users call generic functions with the right types. And you need to have a mechanism for checking that the implementation of functions only uses the contract that you have stated in your concept. Rust does it both ways. C++ only does the first way, which means that now you have duplicated information. You have a concept that repeats your implementation code. And as we all know in software engineering, every time you have duplicated information, you eventually, as the code evolves, get desynchronization, which means that your C++ code is going to say, I can work with any type that has an addition operator, but then it has evolved and now it needs the equality operator. You have not updated your concept and now your concept is useless. In Rust, this doesn't happen. Traits are checked bidirectionally. If you say, I use these properties of the type, the compiler will check that your function indeed only uses those properties of the type. Higher order functions are a direct application of trait. That's a functional programming concept. Remember, Rust is a bastard of C++ and OCaml, where your functions can now take functions as parameters and return functions as results. That's based on traits. Basically, you say, I take any object that implements this one weird trait, which is implemented by function object that have two parameters, one 60-bit integer signed and one 32-bit floating point, and return a new size. And then you can call it with any function, function declared like this at the top level, lambda, anything works. And what we are going to use this for is what I said in the title of this chapter, squaring numbers. Now I have my array. I iterate over it, and I will use a new iterator adapter that I have not talked about before, which is map. What map does is it takes a iterator of things, it passes each thing through a function, and it returns the iterator of results. So here, I take numbers from my array. For each number, I compute the square of this number. And then at the end, I can do anything I could do with an iterator, like collect a vector of it. And at the end, I will get a new vector with all the squares. And the amazing thing is that, again, because iterators are lazy and LLVM, when it wants to, is very clever, this is as optimal as if you wrote the whole vec with capacity for loop pushing thing. More optimal even because it can do some weird tricks based on the fact that it really knows the iterator size ahead of time. Unlike with the for loop where due to things like panics, bad things could happen in the optimization process. Then, you know, one input is not enough. More, give us more power. So then we get the ultimate example for all beginner introductions of this schools courses, the Hadamard product. And here I'm looking at Pierre, which doesn't link to me. No, you can have two vectors. And before, you could do that with enumerate, as I mentioned, but it was bad because you had indexing. And now you use zip. You build an iterator. You call zip. You put the second vector in it. It automatically turns it to an iterator, and then you get an iterator of pairs from both input vectors. And then you can do iteration over pairs of elements. And unlike in last school's edition of GCC, the performance is actually good. Just a problem. If you've ever used zip in any language, you know that a language designer that has a zip must ask oneself two questions. What happens if the two input iterators do not have the same length? And should it be as fast? I answered the second question. To the first question, there are three possible answers, and Rust picks the answer that it iterates based on the length of the shortest array, discarding the elements from the other arrays. If, like me, you think this is the wrong default, there's a library for that. You can get iteration over the longest sequence with empty elements for the missing data, or you can get errors. It's all possible. And with that, Hadamard product, as promised. So with that, we're good. We have so-called map-like operations in functional programming. We can have a sequence, turn each element of a sequence into something else, and we can have arbitrarily complex sequences because of zip. What happens now when you have a sequence of something and you want one result at the end, which is called a reduction? That will be the topic of the next sections of this course, because as you can see, the standard library will give you something, but it's not something you actually want to use if you need floating point performance, which is unfortunate. Well, I'm so bad at timing. Guess I have to do it anyway then. All right, sums. Great, I have an array of floating point numbers. I turn it into an iterator. I can sum it. And because the sum function is generic, it can accept either 32-bit floating point, 64-bit floating point. The compiler is lost. The fallback doesn't work for some reason, and I need to tell it it's going to be single precision. There's just one problem, is that what this will compile into is this sort of loop. You have an accumulator. It's initialized to the neutral element of the sum, which is 0. You add elements to it one by one, and at the end, you return the results. That's very bad for performance. And the reason for that is that compilers are careful, and they don't want to break your computation. And because of that, they never, ever allow themselves to reorder their or modify your floating point operations unless they are GCC with FMA or the Intel compiler with pretty much everything, because the Intel compiler cares about producing garbage fast. What will happen is instead of using all these fancy things I have shown you in the architecture course, SIMD, superscalar, all the things, what you will get is scalar accumulator. Add value to scalar accumulator, add value to scalar accumulator, big dependency chain, you lost all your CPU parallelism and your performance is terrible. How do we fix that? First, this is talking about performance. We set up benchmarks. We have criterion. It makes benchmarks amazing. I mean, too much boilerplate for my taste, but you need to write it once and it stays there forever. And then you can start working. So first problem. So far, I have only taught you about values. Now it's time to talk about references. Because if we only have value, we need to keep creating and destroying heap allocations all the time, and that's not good. That's a deep topic. Basically, C++11 created move semantics. It was done wrong. Rust fixed it. See the chapter for details. So in Rust, when you do A equal B, what this does by default is it moves the value behind B into A, and then you cannot use B anymore. Like, this is what you should be doing if you did std move in C++, except the compiler does not actually check it because the C++ compiler is stupid. What this means is here I have some vector, I assign it, I cannot use it anymore. I pass it to a function, I cannot use it anymore if it's by value. This is excessive for some types, because in Rust, move is defined as memcopy, and there are some types where you can just create a copy with memcopy. So for these types only, we allow C++-like semantics where you do the memcopy, but you still have the original value. But for many types, that's not going to be enough. Let's say you have a type that does not have this copying operation. You want a copy, you know it's going to do a memory allocation, you know that your performance expert is going to yell at you. You have the clone trait. By doing something.clone, you are telling the compiler, okay, compiler, I want copy. I really want a copy. And you are asking, you may be asking yourself, why is this helpful? Why do I need to type more character in C++? And the reason is that in 2 years, when your performance expert is going to be reviewing your code because it does too many memory allocations, he's going to look at your function, he's going to see clone everywhere. He sees immediately what's going on. Whereas in C++, you need to keep thinking, well, is this a reference, a value? Am I assigning to auto ampersand? It's the best. Speaking of ampersand, this is a low-level language. We are going to need some kind of pointer at some point. Cannot live without them. They are too good. The problem with pointer is that pointers break every kind of sanity from programming languages. You can shoot yourself in the foot with them in so many ways. One particular way in which it's particularly easy to shoot yourself in the foot in languages that have pointers is multithreading. So I will get into that. Let's say you have an array and you want to process it with multiple threads. You create threads, you each give them a pointer to the start of the array. You give them an index range and you say you should process elements from this to there, and you get the indexing wrong. You have a problem, undefined behavior. The goal of Rust was to fix this among other issues, like iterator invalidation, for example, which is actually a single-threaded variant of the same thing. And the way they did that is by saying that Rust references are essentially read-write lock. You have a piece of data. If you do ampersand, you get a read-only reference to it. It's actually called a shared reference because if you're doing something weird, you can make it so that it's not read-only. And this is a reference you can share with threads, for example, with many parts of your program. You have many references to the data. But you have checks, which are done at compile time. So the compiler is able to say when you are doing something that's wrong at the expense of sometimes seeing as wrong something that's actually right, because compile time analysis is limited. So let's say you are doing this very classic C++ mistake. Now, I have a function, and I return a reference because my performance expert has told me that all functions should return reference. And what I do inside of this function is I create a value, and then I return a reference to that value. And now I have a problem because that reference points to stack allocated data that doesn't exist anymore. Or at least that's, I wish, what happened. What actually happens is undefined behavior again. So the compiler will optimize code under the assumption that this does not happen, and terrible things may happen as a result. And you don't know what's going to happen. You can switch compiler versions, operating systems, and it breaks in a different way. Another kind of dangling data, so I mentioned iterator invalidation. If you have some read-only reference to some data and you overwrite it, like say you have a vector and you push elements into it, you may have a reference to something that doesn't exist anymore, which is not something that should be legal. So it's illegal. Again, overshooting a bit because this is compile time analysis, so there are some limitations. And in this case, you had a reference to the data, you modified it, and Rust says nope. As soon as you write to something that has a shared reference, all shared references are instantly invalidated, and you cannot use them anymore. That's why I meant by reader-writer lock. At any point in time, you can have one path in the program that has write access to a data, or as many paths as you want that have read access to the data. And if the data gets modified, all read-only references are invalidated. And even if the rules are relatively simple, they can take you very far. This and other properties of references fix all these undefined behaviors that plague C and C++ program and can cause countless security issues. And because this is a performance school, we care about performance. You may be annoyed by the fact that when you are doing numerical computing, you need to put restrict on all your function parameters so that the compiler knows that you're not going to call them with references to the same data. You don't need to do that in Rust. It's implicit to the memory model that I just mentioned. The model that I described, where you have n read-only reference or one mutable reference, is exactly the rules that are imposed by restrict in C. So basically in Rust, every reference is restrict. Problem solved. Not quite. There is a price to pay, obviously. Many traits in Rust that in a higher level language like Haskell would exist in only one version, now exist in 3 versions. One for shared references, one for mutable references, one for own values. This is super annoying. Here are examples of what this looks like in practice. You will read them. I don't have the time. References also interact with functions in interesting ways. There are 3 cases. If your function only takes references as input, that's fine. We are protected by the rule that no reference should outlive the data it points to. So the compiler automatically knows that this function is safe. If a function takes one reference as input and returns one reference as output, then by default, the compiler makes the assumption that your output reference comes from your input reference. Because otherwise, either you're doing something illegal, like returning a reference to something that's on the stack, or you're returning a reference to a global variable, and then Sebastian will yell at you. So it should not be the default assumption of the compiler. If you take multiple references, now you have a problem. To do our static analysis or compile time analysis, the compiler needs to know what the output reference is coming from, or at least what it might be coming from. We could infer that from the code, but then we get something that Rust tries to guard against, which is that by changing the implementation of your function, you can break callers. Because if you say that before the reference came from this parameter and now it came from this other parameter, code that was previously legal becomes illegal. And this is where we get lifetime annotations, which are the way you specify in your API, I, as a library developer, promise that a reference that I return from this function is always going to come from this parameter. If I change it, it's a breaking change, and I should update my library's changelog accordingly and do that as little as possible. Few more rules, but we are out of time. So I will start taking questions. So enumerate, hopefully I have answered that question. It's slightly better. It protects you against the fortran muscle memory. Doesn't do much else. Zip is better. In my opinion, checked zip is even better, but you know, opinions. I lost this argument, sorry. So Yannick is asking Is it time now for all exercise? Well, in an ideal world, you would have more time for exercises. One day is really super short. I can do it. So this ended up being more talk, sorry. What I propose is, if you find some time later, I don't know, you don't know what to do the weekend or whatever, you do them. And if you run into any problem, you ask me. You already have the solutions if you just want the solution. If you want some hints, I can provide hints.